Yes.
Okay. So the relevant literature, the background you can find in these books, basically. And the theorems I will try to mention here also, you can find in these. They're very standard and at least the first three are very standard. About obtaining exact solutions from the field equations, and there are many methods by which we can obtain the exact solution, and one of the very important method is through the least symmetries of the tensors involved in this theory. So we all know the Ricci tensor, the Ricci scalar. I'll be using them in this talk. The matter tensor, because it's basically the talk is about the symmetries of the matter tensor. And it is a symmetric tensor as is the Ricci tensor. And there's the field equation we've been seeing for the last 2-3 days. So we all know what these quantities are. Okay, so by solution we mean this the Riemannian matrix M that satisfies the field equations. So that is the solution of the field equations, and I'll be using this equation 9 without the cosmological constant. Okay, so this is the background definition of a d derivative of a tensor in 11, and the d derivative of any vector u with respect to v given in this equation number 12, and this is accompanied by what is called the Lie bracket, which must satisfy these three conditions: the bilinearity, the antisymmetric, and the Jacobi identity given by 16. So this is the Lie bracket together with this as a result of the definition of the okay. So this 19 gives us the structure constant. So whenever we have a commutator relation between the two, the Lie bracket, it says that we get these structure constants denoted by C, J, K, L, and they are symmetric in the lower indices. Okay, so these Lie symmetries generate in the algebra particularly, and this Lie algebra is characterized by these structure constants. Okay, so this is the background for how do we define the Lie symmetries. So we take any tensor T, this is a general tensor T, and its Lie derivative along V. And if it is conserved, we say that this is the Lie symmetry of that particular tensor. So coming to the particular cases, for example, if this T is a metric tensor and the Lie derivative is equal to 0, we call them as killing vectors or isometries. They're given by 21. And in component form, this equation becomes this killing vector. So X is the vector along which this metric is conserved, or in some sense you can say distance preserving mapping. Okay, so there's some background literature and three-dimensional classification. So another use of these symmetries apart from finding new solutions is to classify these solutions. So earlier I mentioned the book where the different spacetimes are classified according to the Lie symmetries of different tensors like metric tensor and Ricci tensor and so on. So people have done these classifications of three-dimensional manifolds and four-dimensional and so on and so forth. So this is given in the literature. For example, if this is a general spherically symmetric metric, then its killing vectors will be given by these four vectors, 24, 25, 26, and 27. So first one actually defines staticity. So if it's a static, we will have this time-like killing vector, otherwise this is actually the definition, geometry definition of a sphere. So these three define a sphere, and the first one defines the static sphere. And similarly, if we, okay, so this is a particular case, this is a case of another cylindrical symmetric line element, and the symmetries are given by 29. The first again is the staticity, and the two define the cylinder. The, the symmetry, with respect to angle theta and z. So this is, and the particular case of cylinder can be considered as a plane given by 30, where the coefficients of y and z become equal, so this becomes a plane. So this has more symmetries, as you can see. So in 31 it has 3 killing vectors, and if we add another one, the time like, it will become a static plane. So these things define the geometry and whether they are static or non-static. So similarly, if apart from the metric tensor, if we use the Ricci tensor, so its symmetry is known as Ricci collineation. So 32, the RAB Ricci tensor is just replaced with the metric tensor and it becomes a Ricci collineation, and 33 gives the same equation in component form. And similarly, if we replace the Ricci tensor by the matter tensor, it will get the, what I call the matter collineations. And I will mainly be concerned about the relationship between this Ricci collineations and matter collineations. So this is an old subject, as you saw from the references. And so on, this is the fourth rank tensor, the curvature, and the symmetries will be given by this equation, the symmetries of the derivative of the curvature tensor, and the equations will be much more complicated and so on. And for the Weil tensors again, mathematically it's a 4 rank tensor, that the equations are very much more complicated. And in the previous definitions, I took the right hand side equal to 0. If it's not equal to 0 and it's proportional to, for example, the metric tensor again, then it gives rise to the conformal killing vectors, depending upon what this psi function is. If it's constant, then we call them self-similar or homothetic spacetimes. Otherwise, if it's a general function of spacetime coordinates, it's called conformal killing vector. And similar symmetries can be defined for other tensors also, but I will not go into those. So this is a homothetic motion. And for the killing vector, now I come to the dimension, what is the dimension, and then I think you'll need to state some theorems, standard theorems, for example. So this, if this is an affine tensor, the least symmetry is of space-time, which means 4-dimensional manifold. So the Lie algebra, this is generated by the Lie symmetry, the dimension will always be less than 20. And the second theorem says that the killing vector is always less than homothetic vectors.